Today, we are diving into the art and science of fusing metal. You know, it's a process that is literally the backbone of our modern world, holding everything together from the tiniest electronics all the way up to the most massive skyscrapers. So how does it all stay together? Let's find out. I mean, just take a look around you. The phone in your hand, the building you're in, the car you might have driven today, all of it depends on joining pieces of metal together with really just incredible accuracy and strength. But how is that actually done? How do we create these bonds at a molecular level that can handle just immense forces? Well, that's exactly what we're going to break down. So here's our game plan. We'll start with the basics of what it means to join metal. Then we'll compare soldering and brazing. After that, we're diving headfirst into the world of welding, talking about the tools of the trade and even the welder's unique language. And finally, we'll connect it all back and see why this level of precision is so unbelievably critical in our day-to-day lives. All right, let's start with a really simple analogy. At its heart, every single technique we're about to discuss is all about one thing: creating a powerful, permanent bond between metal parts. And, the best way to think about it is with something you've probably used yourself. Now, that phrase hot glue is a fantastic starting point, but we're doing a bit more than just sticking things together. See, the glue in this case is a special filler metal, an alloy, that literally creates a bond at the molecular level. This fusion is what gives the joint its insane strength. It's really less like gluing and more like making two separate pieces become one single piece. Okay, so let's jump into our first two methods, soldering and brazing. They are very, very similar processes, but they're separated by one single critical factor, and that's temperature. And here it is, the magic number, 450 degrees Celsius or 840 degrees Fahrenheit. Now, this is not some random number. It is the official dividing line. Any process that uses a filler metal that melts below this temperature, that's soldering. Anything that melts above it, that's brazing. It's really that simple. This slide really shows you the difference in action. Over on the left, you've got soldering on a circuit board. That low temperature is absolutely perfect for this kind of delicate work, where just a little too much heat would completely fry those sensitive components. But then on the right, you see brazing on a bicycle frame. Here, the much higher temperature creates a way stronger bond, which is, essential for something that's going to take a lot of stress. So this chart gives us a nice little summary. The key takeaway is this: while both are used to join metals without melting the actual pieces you're working on, brazing is generally going to give you a stronger joint, but it's also more expensive. Soldering, on the other hand, is cheaper and a whole lot safer for those heat-sensitive jobs. It's all about picking the right tool for the job. Okay, now it's time to turn up the heat a lot. We are moving into the world of welding, and unlike soldering and brazing, welding very often involves melting the base metals themselves, causing them to fuse together directly. This is how you create the absolute strongest joints possible. One of the classic types is gas welding, and the perfect example is oxyacetylene welding. So why that specific combo? Well, because when you mix oxygen and acetylene, you get a flame with a ridiculously high temperature, hot enough to melt steel, which needs about 1,500 degrees Celsius or over 2,700 degrees Fahrenheit. We're talking about some serious, serious heat here. But it's not just about getting it hot. A skilled welder has incredibly precise control over that flame just by adjusting the gas mixture. A neutral flame, with that 1-to-1 ratio, that's your go-to for most jobs. But if you pump in a little more oxygen, you get a hotter, oxidizing flame, which is great for metals like copper. And if you add more acetylene instead, you get what's called a carburizing flame, which can actually add carbon to the steel, a very specialized technique. And check this out. As you can see right here, even within one single flame, the temperature varies wildly. That super bright inner cone can be over 3,000 degrees Celsius, while the outer part is way cooler. A welder uses these different zones with incredible skill, moving the workpiece closer or further away to control the heat input second by second. It is pure craftsmanship. So we have our heat source, but what else do we need? Let's talk about two things: the filler material, which usually comes in the form of a rod or an electrode, and the raw physical skill it takes to weld in all sorts of different positions. This thing right here, this is a stick electrode. And believe me, it is so much more than just a metal wire. The metal core on the inside provides the filler that actually becomes part of the joint. But the real magic, it's in that outer chemical coating, which is known as flux. The flux is basically the secret sauce of a good weld.
As it burns away, it's doing several critical jobs all at once. It creates a shielding gas to protect the molten weld pool from all the oxygen and nitrogen in the air, which would totally weaken the joint. It also forms this layer of slag that floats impurities to the surface. And, on top of all that, it insulates the weld, letting it cool down nice and slow so it doesn't become brittle. Now here's where skill really comes into play. As you can see, welding isn't always done on a nice, flat, convenient workbench. Welders have to be absolute masters of these 4 basic positions. Sure, flat is the easiest, but just imagine welding vertically up a wall, or even worse, overhead, where gravity is literally trying to pull your molten metal right down onto your head. This takes an incredible amount of skill, control, and tons of practice. Okay, so mastering those positions is one half of the skill. The other half is understanding the language of the tools themselves. The world of welding is just filled with these codes that tell a welder everything they need to know. It's kind of like a secret language, and we're about to crack it. Take a look at this common electrode, labeled E7018. It might look like a random jumble of letters and numbers, but it's actually a perfect set of instructions. E just means it's an electrode. Easy enough. 70 tells us the finished weld will have a tensile strength of 70,000 psi. That's how much pulling force it can take before it breaks. The 1 means it's an all-position rod, and that final 8 tells you exactly what kind of flux coating it has. See? Every number has a job. Speaking of currents, another hugely important concept is polarity. Now, this simply refers to the direction that the electricity is flowing in the welding circuit. And trust me, which way that current is flowing makes a massive difference. So with direct current, or DC, you got 2 choices. DCEP, or electrode positive, concentrates about 2/3 of the heat right on the electrode's tip. This melts the electrode faster, which gets more filler metal into the joint really quickly. On the flip side, you have DCEN, or electrode negative. This reverses everything. Now, more of the heat is focused on the workpiece, which gives you deeper penetration into the metal. Choosing the wrong one can mean a weak weld. So the big question for the welder is always, where do you need the heat? Wow, okay, we've covered a lot of pretty technical ground here, from temperature thresholds to chemical coatings and electrical currents. But why? Why does all this incredible, painstaking precision matter so much? It's because every single one of these little details contributes to the strength, the integrity, and ultimately the safety of whatever is being built. That simple 45-degree line determines if a joint is meant for a delicate circuit or a load-bearing frame. That code on an electrode guarantees the weld is strong enough for the job. These aren't just abstract numbers. They are guarantees of performance that we all rely on every single day without even thinking about it. So the next time you cross a bridge or use your laptop or even just sit in a chair, maybe take a second. The world we've built is held together by countless invisible, perfectly controlled moments of fusion. And now you know just a little bit more about the incredible art and science that makes it all possible. Will you start to see them? The invisible fusions that hold our entire world together?